I am at the Diagnostic Training Manager for Worldpac Training Institute. Basically, what we're going to go over in this class is turbocharger oil consumption and what causes it. A lot of people think that a turbocharger goes bad and that internally that there's a seal or something that degrades, and then we end up with a oil leak situation. It's a lot deeper than that. So we'll go through everything that's inside of the turbo so that you understand what parts are there and then what failures they may be. And then we'll also, lay to rest some of the myths with turbos and stuff like that, as well as go over the physics behind it. So just a little bit of housekeeping. If you have any questions, just unmute yourself and ask questions as I go through it. Since this is the platform that we're on, it's easy to do so. Don't be shy. No question is a dumb question. So always feel free to ask and I will answer it the best that I can. So start out, first thing we're going to go over is all the internal parts of a turbocharger, all the mechanical parts, how each one of them works, some of the idiosyncrasies with them and things like that. The first main component is a actuator. Basically what the actuator does is the actuator is going to open the exhaust wastegate on a internally wastegated turbocharger. It can be mechanical, it can also be electronic. The most simplest ones are going to be mechanical, like the ones you see on the screen. I don't know how much you guys can see me, but I'm going to hold up some of the parts as we go so that you can also see that. When I get to an important part, I will stop sharing my screen. But there's a part in real life if you don't want to look at the pictures. So basically there's a rubber diaphragm inside of this. It can either be actuated by vacuum or by pressure. Most of the ones you will see are going to be actuated by the pressure of the turbocharger, and it's going to be attached to the intake side of the turbocharger. As boost builds, it's going to go in and it's going to take boost pressure. Get my laser pointer here, and the pressure is going to go into this little spout and push on the diaphragm, and then this is going to start to extend. So the really important thing behind an actuator is typically there is no specs anywhere on them. So you should not adjust them. If you adjust them, the odds of you getting it adjusted back correctly are very, very slim. Some are not adjustable, like this one in particular doesn't have any threads on it, so you don't have to worry about that. If you ever do take one apart, the way that they are adjusted is you pick your spec of where you want the turbo to start opening the wastegate. So typically you're looking at like max boost pressure. Let's say on an EcoBoost, normally it's somewhere at like 6 PSI where they start to open. So you would take a regulator and put 6 PSI to the spout right here, and you would allow this to then extend, and then you would adjust this until you had it able to slide onto the wastegate. You're going to hold the wastegate closed and then slide the actuator on. So what I'm talking about, if you guys can see on my screen here, and we'll go over this more in depth in a minute, but there's the wastegate, and basically all that's going to happen is this actuator arm is going to sit on top of it like that. So you're going to hold it closed, open position, closed position. When you're adjusting your actuator, you hold this closed, put the pressure on your actuator, and then adjust it in until it slides on. And then when you take the pressure away, then it's pulling tight because of the spring pushing back on it. And that's what some people refer to it as preload. So if it's not set right, you can end up with two different things. You can end up with an underboost where it's set to the point where it opens at say 2 PSI and it always is open at that point pretty much, or you can have an overboost code where somebody's gone on a forum somewhere and someone told them, hey, if you adjust your actuator, make your car faster. So that's not a great thing to have happen. I had a Focus, Focus, I think they're RS or something about a month ago. A guy and his buddy had messed around with his track car and put an aftermarket actuator on it, did not adjust it correctly and didn't know how to adjust it. So they stuck it on and blew a motor up in it. The shop that I went to look at it at put the motor in. It lasted approximately a week and then started misfiring again. I got called out to see why it was misfiring, and it was misfiring because They put the same turbocharger back on and blew up the second motor. So it's a very simple component, causes really catastrophic failures. So keep that in mind. The electronic ones aren't really adjustable, at least to the everyday Joe without tuning software. So that's not as big of a problem on that. Next is the compressor housing. Compressor housing is the intake side of the turbo, but as we go through this, we're going to call it the compressor housing. That's what it's called in the turbo rebuild industry. There is a contour in it, and it's made of a very, very soft aluminum. So the contour, as you can see right here, is where the wheel sits, and that's a very, very, very tight tolerance. If something gets in there, typically it's kind of ruined. You can, if you were a rebuild facility, so let's say where I used to work D&W Diesel, when we would rebuild these, some of the contour profiles we had measured out, and the welders would TIG weld those up and then they would remachine them. But for most of us, the guys that aren't rebuilding them, if something gets down in there and they get hit, you're screwed. That's pretty much it. You can try to, if it's something that has only hit it a little bit and just left maybe some pits in it, you can take a flap wheel and clean it up a little bit, but you have to be really careful of the gap that you leave between the wheel and then the housing, because if that gap gets too big, then you can have other issues. Turbine housing is the exhaust side. This is the hot side. So because of that, it's made out of cast iron. This is where the wastegate is housed, like we talked about. So wastegate is right up here. And one of the things that we have to talk about here is, you see on this one, this has got a little crack in it. So a lot of people think that that crack means that's bad. That crack will show up about probably a month into a turbo's life. So the crack is not a sure thing that it's bad. It's pretty typical of most turbos. When that becomes an issue is when that crack starts to open and you start seeing chips out of it. So you can see this one is a pretty uniform crack and it doesn't look like there's any chips missing. It's spreading a little bit up there. But once these get to where you can look at it and say, like, one side of the crack no longer looks like it will line up with the other side of the crack, like more metal has broken away from it, that's when it's an issue, because at that point, now the wastegate is not sealing. And the bigger issue is that those small pieces of cast iron have now gone down into the turbo, or could have potentially gone down into the turbo. So that would be, catastrophic. A turbo spinning at 200,000 RPM or 250,000 RPM, and anything that gets inside it is detrimental. So the other thing is that wastegate is not a perfect seal. So don't expect, I've seen some people try to pressurize the exhaust and look and see if you have bubbles around the wastegate. You're always going to have bubbles there. It's not a perfectly machined surface by any means. One thing that can happen there on like Mercedes, like Garrett turbos and stuff on those, it's real common that wastegate can wear. So what'll happen is on this flap, it'll get to where it moves kind of side to side and this shaft is cocked. And when that happens, then it doesn't seal at all. So if that happens, then of course you're going to have exhaust gases escaping and you're not going to have any boost building. The other thing that happens in Rust Belt regions, Lucas, you guys being in the mountains, this will happen. If something sits, guys that tow campers, they buy a truck and it's seasonal, they drive in the summer, in the winter they put it up, this wastegate will stick, it'll rot. Once that happens, you can take it apart, you can free them up, but if you're on most stuff, it's so hard to get to the turbo that if you're gonna take the turbo all apart to do that, in my opinion, you're probably better off just selling them a turbo. But it is doable. You can heat them up and free them up. It's not like a huge deal, not super hard to do. Again, if you take that off, just make sure that you don't go and adjust the actuator that's attached to it. Bypass control valve. This is not going to be on every turbo, but it is on a lot of stuff, a lot of newer stuff you'll see it on. This is on a cruise turbo. The little Honda new 4 cylinders, they have this. Some of the Ford turbos have this. Basically what we're doing here is boost pressure is built up really high, and then somebody lets off the accelerator. Well, when that happens, we don't want boost pressure slamming into the back of the throttle plate. If that happens, you get what's called turbo surge, and then you'll get a really weird like whooshing sound it's not great for the turbo. It's obviously then not great for the intake either, because you could have, let's say 15 to 30 PSI maybe pressing against that throttle plate. So what this does is, as soon as it sees the throttle position sensor close, a signal is sent to a solenoid that's duty cycled by the PCM, and it will send engine vacuum to it. And when engine vacuum goes right here, it will pull this diaphragm open. And when this diaphragm opens, we end up recirculating the boost to the intake side, and it just makes a loop. And because of that, then we don't build any boost when that's open. One thing to note, this is on a Chevy Cruze here. There's a lot of Cruze stuff in here because we have tons of issues with these. This will relate to any vehicle that has this. This one had oil in it. What happens is, we'll go over the failure that causes this on any turbo. If a turbo has got oil on the intake side and it can sit down here and pull into this. Now, as you see, we're on this side of it because you see the oil here. So we're over here. That means that if this were to try to pull open, there's liquid here. So we no longer can move this to the open position because it would be trying to compress liquid. So when that happens, now you can end up with turbo surge because that valve is no longer working. It's easy to take off. It's 3 screws on this one. Most of them, it comes right off. I can't speak for every turbo out there. Most of them you can buy just the parts. Also, most of them are like a neoprene, so the oil really doesn't seem to hurt them. So most of the time you can wash them. But you can normally order those parts separately. Even if, let's say, GM didn't have it, if you were to find the manufacturer of the turbo, you could call a rebuild facility like where I had worked, and be able to find the part numbers for that, say from Garrett or BorgWarner or something like that. So that's an option, and note that if you have turbo surge, that's something that you need to look at. Next up's the compressor wheel, or the intake side of the turbo. Again, intake side is cold, so the compressor housing is aluminum, the compressor wheel is aluminum. It's very, very, very brittle. So if anything hits it, it's pretty much junk. You can try to bend the fins back, but it's so brittle that typically the tips of the fins, if they get touched by anything, when you try to bend them back, they break. The other big thing to consider with this, and this is very important because they're out there to buy, is this is a balanced component. So this little dot right here, that is a balancing spot on it. And there's also, you can see over here on this one, I think, I can't see my picture. I gotta move my screen. This one up here, you can see it. At the very tip of it, there's an indent, and that is also a balancing spot. So let me zoom in on that for you. This little spot right here is from balancing. They just grind on the wheel. So the thing to remember is, not only is this wheel balanced, but it's going to be balanced as an assembly, and we'll talk about that more in a minute. So most of the times when you're building, it's real popular in the diesel side, you'll see like from a company, I think it's called Wicked Wheel, you can buy just the intake or just the compressor wheel. If you do that and you install it and the turbo is not balanced as an assembly, it is no longer balanced. So even though that wheel is balanced, the intake side or the compressor wheel is balanced, the exhaust side, the wheel and shaft, I'll show you in just a second, is balanced, then they're put together and balanced again as a cartridge. So we'll talk about that here in a second. This is the wheel and shaft. The wheel and shaft is, again, the exhaust side. It's a couple different types of metal that they're made out of. Typically, they're a nickel alloy that's also really brittle and really, really hard. If they get hit by something, sometimes they're okay, but they can bend. And once they bend, then they don't balance, and it just becomes a nightmare. As you can see, that red arrow that we got on it, there is a ring. So this ring that you see here is a metal piston ring, as we would know it. It's really no different than a piston ring on a piston in an engine. It's metal. That is the only seal or only type of seal that is in the engine. There is no rubber seal. So as you can imagine, with a piston, when we do a leak down test and we have, let's say, 20% leakage, and that's acceptable, the air is escaping past it because there's a gap at the end of the ring, just like you can see up in the top right picture, there's going to be leakage by these rings. So they are not an oil seal. They're just a ring, and they're there for nothing other than to keep dust out. And I'll show you a video to further explain that here in a little bit. One thing that can happen is the exhaust side of it can coke up and the oil can start to turn into carbon. And when that happens, you can see where this arrow shows the ring is really loose. So that's not good. This is basically poor maintenance, and a couple other things we'll talk about. But what will happen is that carbon is really hard because it's basically getting hot exhaust air blown over it. So think about taking graphite or carbon and grinding it up and then continually spinning something through it at 200,000 RPM. It ruins stuff, even nickel alloys. So we do need to be aware that the component can go bad, the ring can go bad, and then the bearing housing itself, we'll talk about in a second, can also be worn out from that. This is also balanced. As I was saying before, we balance the compressor wheel, then we balance the wheel and shaft, and then you put them together as a component. And once they're together as a component in a cartridge, then they're balanced again. So on the intake side, the compressor side, there's also a flinger and thrust collar. The flinger, as you can see, also has a pinion seal on it, or a pinion ring on it. So, or sorry, not pinion ring, piston ring on it. Can't talk tonight. So this is another one. You can see this is worn out. This was worn out because of low oil flow to it. There's oil that comes down into here, and it's supposed to keep this cool, comes through right here. And a couple different types of designs that are out there, but there is supposed to be oil that is just kind of a splash effect on it. Not a lot of oil. It's, like I said, simply there to keep a little bit of oil on this to keep it cool. So you can wear from lack of maintenance. Again, that is the only seal on the intake side. That is the only seal on the exhaust side. So it's very important to understand that there is no rubber seal in any turbo out there. They all use this. Some of them may use 2 or 3 piston rings. Most are going to use 1 or 2. I would say the majority use 1. The only one really that you'll see that uses 2 in automotive is a 6.7 Ford diesel. Everything else is pretty much going to use 1. So I'm gonna play this video. You won't be able to hear the audio from it. So as I play, I'm just gonna kind of skip through it a little bit. What he's gonna do here is this cartridge is set up with no seals, no piston rings in them. So as we go through this, he's gonna show what happens.
So there's nothing to keep the oil in. So this is without a seal in there. And so there's nothing to keep the oil in. So just to show you that there's actually no oil pressure on any of the seals, and they don't have any contact with oil as well. So I'm going to simulate what it would be like in the car.
You guys cannot hear the audio from that, correct? Okay, that's what I thought. Yes. So what he's done so far, so this is set up now. This is the flinger right here, like we talked about. There's no seal on it at the moment, so no metal ring on it at all. And what he's going to do is he's going to turn the oil on, do it here in a second, and I'll show you that. And you're going to see that no oil comes out of that, even without a ring. So this is the drain tube on it, and oil is going to come up through here, and then flow through it. So you can see the oil coming out of it right now. You can also see that he's got no oil coming out from the flinger, even though there's no metal ring in there right now. So the next thing he'll talk about is going through and showing what can happen and what can cause some oil to go out. So say your drain tube wasn't in the right spot. Watch the oil right here. So you can see oil come out. All he did, he didn't pinch the drain tube or anything. He just lifted it up. So how can that happen? Well, the bearing housing on a turbo can move. So let's say this bearing housing that he's got over here, right here in the center section, let's say that bearing housing was twisted and was in the wrong spot. So your drain tube now was twisted. When that happens, now the oil is not going to flow out of there correctly, and it's going to pull up and come out of that. And I'll show you in a second why that happens when we look at a cutaway of a bearing housing. So the other thing that can happen is people like to put these type of fittings in it. A lot of guys, the performance guys, will use those AN style fittings. They're not big enough. So the flow for the turbo is determined and the drain tube is built for it. So if you go and switch to a different type of drain tube that doesn't allow enough drainage, now that bearing housing isn't going to drain out fast enough. So that's going to be potentially a big issue. So we'll talk about how that happens when we look at the bearing housing here. Get out of the video here. Okay. So the oil runs down onto the bushings inside the turbo. That's the other thing that's interesting is the inside of a turbo, a lot of people think has bearings. Very, very rarely will you see it have a bearing. Most of the time you're going to see it have brass bushings, sometimes one piece, sometimes two. And then sometimes they'll have a thrust bearing on it like you see here. And that's basically your thrust collar right here rides against that. So as you can see, there's supposed to be oil that comes in here to keep this all cooled off and keep this lubricated as it spins against it. The oil is also supposed to lubricate these brass bushings. The bearing housing is the important part of all this. So I was talking about the wheel and shaft can wear a groove in it, and you can see a groove is worn in this one right here. And then it's set up as a cartridge. So when it's set up as a cartridge, that's when it's going to get its final balance, as I was talking about. So you're going to balance the compressor wheel and then the wheel and shaft, and that's going to be put together in this cartridge, and then it's going to be mounted in actually the contraption that the guy on the YouTube video is just using that as a balancer. So then it's going to be spun at speed, and when it's spun at speed is when it's going to be balanced its final time. So why is it so important? Well, the inside of the bearing housing looks like this. This is if there's one takeaway from this class, this is going to be it. So your sealing surface for those rings is right here and right here. Oil comes in here and it goes through this little gallery, goes out onto your bushings, and then it just drops off here. So essentially you want atmospheric pressure in here so that the oil can run and just drain here and just drain here. So the other thing that can happen is, this is another type, you can see it come through here, drain here and here, goes through your drain, and then comes out here. The other thing that can happen though is, let's say you have high crankcase pressure. If you have high crankcase pressure, imagine trying to blow through a straw and you're holding it up to your mouth and you're trying to blow water through that straw, and somebody walks up with an air compressor or an air hose and sticks it in the end of the straw and puts 120 psi in it, it's going to obviously blow back at you. So your oil pressure is coming down in through here, but you don't really know how much pressure you're going to have there. Hopefully you're going to have engine oil pressure, but we know that maybe engine oil pressure can be, let's say on an old GM. So we'll use that as an example. Maybe at idle, it's going to drop down to 10 PSI or something like that. If you had a crankcase pressure problem, you could certainly be higher than that. We would hope you wouldn't be, obviously. Hopefully you're not over a pound in crankcase pressure, but that is a possibility. And if you have pressure here, or this line is clogged, then it can't drain. So the other big thing to take into consideration is the size of those oil galleries. So as you can see, those look pretty small. Well, I'm going to turn my PowerPoint off here and I'm going to show you just how small they are, because in the picture sometimes it's tough to tell. Let's see. You guys all see me on full screen now? Okay. So, tip of a pen. That's the oil gallery. It's smaller than the tip of a pen. So I'll show you on the other bearing housing, the other style. I had what looked to be a little bit bigger one. Again, that's all it is, the size of a pen. So imagine with carbon getting in there or oil sludge getting in there, that's a really, really, really small gallery that any, poor maintenance on these and correct maintenance on these is going to be a problem, because that oil gallery is going to get clogged. And once that's clogged, no oil is going to get to the bushings. So that's a huge, huge, huge problem. So if there's one takeaway from the class, it's going to be to remember about the bearing housing and how the bearing housing works. All right, the other important thing to notice with this is a coolant passage that's right here. So coolant flows through the exhaust side of a turbo. The reason for that is to try to cool this end of it to help keep the oil from burning, sludging, and coking up. As you can see, this gallery is full of rust. So once that happens, you now no longer have coolant flow going through it, and the exhaust side of it is going to get really hot. Once the exhaust side of it gets really hot, now you're going to start burning oil and coking up oil on that side and ruining the ring on the wheel and shaft. Some vehicles also have after run, so we're going to run a coolant pump, or maybe we're going to run the cooling fans after the vehicle is off to continue circulating that to try to cool that turbo down as the vehicle is cooling down. So BMWs, that's something that they do. We have to keep in mind there's some problems that will happen with that, and we'll talk about that a little bit later on. So there has to be coolant flowing through it. The other thing to keep in mind is on that particular turbo, a lot of people like to talk about that you can mix coolant and oil in a turbo. And I want to stop and share this again because this is kind of important. So some people have talked about that you can potentially have an issue in a turbo where you have coolant and oil mixing. Fortunately, that's really, really, really hard. So coolant goes through there, and then in return is going to come through that passage. You can actually kind of see me through the passage, so you can see my finger there. You can see right down through there. So you're going to go through this passage, go through here, make the loop, and then in return, once you go through that, you're going to go right back out. So the only way to end up with coolant and oil mixing inside of a bearing housing is if this bearing housing were to crack, which I personally have never seen happen, and I've probably rebuilt in the realm of, I don't know, 10,000 turbos or something when I was doing it full time. So I've never seen one crack. So it's very unlikely if you have coolant mixing in a turbo that you could have a bearing housing problem causing it. So just keep that in mind. So as a review of all the parts, the bushings, thrust bearing, flinger, compressor wheel, and wheel and shaft, and then the sealing rings. So as we talk about stuff, just remember those components because that'll make it easier as I go through this. This is what it looks like when it all goes awry. This is out of a Chevy Cruze. Again, you can see coking right here. You can also clearly see this is kind of a strange design too. Most of the time they don't look like this. Most of the time there's at least two bearing surfaces. The Cruze only has one, so it makes it even more susceptible to this. But As oil stops getting to the bushings, this locks up, and in return at 200,000 RPM, when the shaft stops, the wheel does not, and the wheel just snaps off. And at that point, now you have a direct path for oil to flow out into the engine. So, do we have any questions so far? All right. I'll minimize this so I can see everything here. So, what causes oil consumption then? If we don't have seals in it, how do we end up with oil? So there's a couple different things. When a turbocharger is trying to create more airflow than what the intake system can supply, we end up with a vacuum that will build inside the intake tract. So think of a turbo is a vacuum. We've all seen the Dyson commercials, and they talk about using turbo technology. That is basically they're using the intake side of a turbo and spinning a compressor wheel with an electric motor. So a turbo, even though it builds boost, you need to think of a turbo as being a vacuum first, because without intake air, you don't have any boost. So the first thing a turbo has to do is accomplish a vacuum and pull air in. If an air filter becomes clogged and it's trying to pull air into it, then we end up with an issue and we start to pull the intake side of it down into a vacuum. So the other side of it is it can happen when it's been modified and it's supposed to make more boost, and then let's say the intake or the exhaust aren't upgraded. So I used to see this a lot on the diesel side of it. Kids would straight pipe the truck and then they wouldn't do anything to the intake side, and they would tune it. So they'd leave a stock air box, a straight pipe, and a tuner on it. It's flowing more fuel, also flowing more air out of it. And in return, now it can't bring in enough air to make up for the rest of the engine. So then you end up with a vacuum again on the intake side of it. So things to think about that you need to, as you increase horsepower, increase fuel, increase air out, that then you need to also be able to increase the volume of air that's going to go into the turbo. If they don't, and we end up with that vacuum, we're going to refer to it as a pressure differential. So think about it that you have above atmospheric pressure on the exhaust side. So the exhaust and intake side are going to be between, so from the turbo to the exhaust manifold. So the exhaust comes out of the exhaust manifold, goes to the turbo. That section between those two is always going to be the same pressure as the boost side. So if you have a back pressure sensor like on the Ford Transits, and that sensor's between the turbo and the manifold, that's why you'll see high pressure there, because it's always going to mimic the boost pressure side, because it has to be the same pressure on either side of the turbo since there's no seal to hold the oil on the inside of it. So when we end up with a pressure differential, what we can end up with is you still have exhaust pressure on the exhaust side of it, but now the boost side of it isn't able to make boost, and that pulls into a vacuum. So now you're pushing from one side and pulling on the other, and we're going to push the oil and pull the oil into the intake side. So once that happens, then what do you think? Where does the oil end up? We'll go through a case study quick to get you thinking about that. So this is a 2013 Cruise with a P0299. This is a low boost code. Key on engine off on these is 14.7 PSI, roughly. It's like 14.6 atmospheric pressure. So knowing that anything below 14.7 PSI, shown on the map sensor or on the boost pressure sensor or barrel or anything like that, 14.7 is key on, engine off. Anything below 14.7 is going to be in a vacuum. So 10 PSI is really a vacuum, because then we're really 4 PSI of vacuum. Anything above 14.7 is now boost. So if you look at this picture, this was taken at 3,840 RPM. This is a case study that's on ScanShare. It is not mine. I think it was Phil Furnier's. and he just put the data up there on it in the code. So wanted to show you how you can tell what's going on by looking at scan data, and then also start to think about, again, where's the oil going to end up and what is it going to cause. So engine speed of 3,840 RPM. You see the mass airflow came up and then it just flatlined at 11.44 grams per second, which we know is really low for this at 3,800 RPM. Map sensor shows 5.2 and boost pressure shows 5.3. So we know that the intake is in a vacuum, and we know that in the boost or charge air pipe, we are also in a vacuum. This is from a known good car. You can see at 5,500 RPM, we're at 119. We were only at 11 on the other one. You can also see that we're at 23.9 PSI where we were at 5.9. So this one is 14 is going to be where your 0 point is. So we know that we're 6 to 20, another 3.9. So we're, what's that? 10 PSI roughly of boost pressure. And then the other one, because we're at 5 PSI, we're roughly 9 PSI of vacuum. So what do you think could cause it? Unmute your microphones. Tell me what you guys think.
Intake restriction.
Okay, why do you say that?
Because the mass airflow sensor is not getting the correct reading, which in turn would throw the computer to freak out all the other sensors, pretty much.
Oh, okay, so you're very close to that. You're really, really close. Your reasoning, I'll help you with. So what we see is this is the same cap or same car, just at a different point. We're going to look at it at 2,900 RPM. Throttle positions open 100%. So when the throttle is open, this is the other thing to take into consideration. When you're looking at a turbo car, I go over all of this in a lot greater detail in the 4-hour class because this gets into the diagnostic side of it. But to quickly talk about it here, you want to check your sensors, your boost pressure sensor, your map sensor, baro sensor, all against each other. So you want to do key on, engine off, and make sure they all match. Then you want to start the vehicle and you want to run it up full throttle. And you want to make sure that when the throttle plate is open, that they match. Because if the throttle plate's open, now your boost pressure sensor and your map sensor are all in the same tube. They're going to be connected at that point. So long as it's open at 100%, they should match, and that's how you know that the sensors are okay. So this vehicle, again, we see that it topped out 12 grams per second. What we also saw is the engine tried to build boost here. So this is the actual reading. The sensor hasn't, your readings on these sensors, the computer won't change them. The only way for a computer to change these to something other than what they actually are is if a tuner was to go in and mess with the algorithm. And typically when they do that, they'll lock them in a position to make it think that it has lower boost than it does, to make it keep building boost. So this is going to be actual. So you see it come up. We tried to build boost, and at the same time, we tried to flow air into it, and then we stopped. This is where we stopped. Once we stopped, we started pulling down into a vacuum. So the reason that we're pulling down into a vacuum is because we can't pull any more air in. The engine's constantly turning, the engine's an air pump. It's trying to pull air in. It's turning the turbocharger. In return, that turbocharger is trying really, really, really hard to pull air in. No air is moving past the mass airflow sensor. No air is moving anywhere in the car. So therefore, now we've pulled into a vacuum. So because the vacuum's beginning to build in the intake and the throttle plate is open, we know that that means that there's an intake restriction. Boost can't be achieved because we can't pull any air into it, which is why you see the mass airflow number is low. So the mass airflow is low because air stopped flowing. We weren't able to bring in any more air. Think about, take a really deep breath. You get to the end of your breath and you can't take in any more air. So you stop being able to pull air in. That's exactly what happened with this vehicle. because the MAP sensor is below atmospheric pressure and MAP and boost to match, we know that those sensors are correct. So we know we don't have a sensor issue, and we can look and see that the mass airflow also stopped seeing airflow. So at that point, we know that we have an intake restriction, and that's why that it's pulled into a vacuum. Does that make sense to everybody?
Yeah.
Perfect. All right, this is where it starts to get pretty neat. When a intake restriction happens on a vehicle, now this is going to be whether it's on a non-turbo or a turbo. If you were to take and put your hand over the intake of a car and step on the gas, you would pull that whole intake system into a vacuum, because the engine is a vacuum. When you put a turbo on it, it's just an even bigger vacuum. So in return, anything that's on that intake side with a vacuum pulled on it could possibly collapse, like this air filter. This air filter for this particular thing was just too small. It's on a 5.9. That's too small of an air filter for that, so it pulled in. But what's interesting, this is on another Cummins, that's a stock air filter, and this was also on a stock truck. You can see it's dirty, but it doesn't look really dirty, or at least not at first glance. So as that gets sucked in, you can see it just starts to collapse that filter, and then in comparison to the new one, that's all it took was some silt. This was, I think the guy that posted the picture said that this was a truck that runs for like natural gas refineries. So the filter doesn't look really that dirty. I mean, you can even see, let's zoom in on it a little bit. You know, this area up here is still pretty white. It doesn't look really dirty. So all up here looks okay, but then all in the bottom of the pleats is like that. And that was enough to cause it to collapse. So we're pulling a vacuum and collapsing a filter, and talked about making that pressure differential to where we can start to suck oil out. If we get enough vacuum that we can collapse an air intake hose like this one here, don't you think we can create enough vacuum there to suck oil through the turbo, since there is no sealing ring in it? When this happens, there's some other things that we need to take into consideration. That being the PCV system. Does the vehicle have a PCV system? This is on a Chevy Cruze, but other vehicles also use this type of system. A lot of the like Mercedes and things like that can also use it. The PCV hose is on the intake side of the turbo. So you see right here, this is where this would attach to your air filter, go out to your air intake box. This is the PCV hose. So it's right here, goes right over to here, and then goes to the PCV system. So has anybody ever had to put an intake on a Cruze before? For, let's say, a P0171 code or something like that?
Yeah, a lot of them. And the hose that goes with it.
Yep. So you're going to get to learn right now why this happens. And the GM engineers didn't seem to catch on to this, because obviously the service bulletin tells you to replace the intake. And if it's ruined the valve cover, then also to replace the valve cover. And that's because that little seal disappears. So it's just a small silicone seal that's down in there. It's not really a seal, it's a check valve. So it gets oil soaked and then it gets soft. And when that gets soft and you have vacuum coming across this, what do you think happens if this gets plugged? Where does the vacuum end up? It ends up right here. So I'm going to show you how we end up from here to here. So anybody, what do you think is going to happen, or what do you think it could do?
Turn your turbo into a salad shooter on a bad day.
Yeah. So I'm going to stop sharing my screen here. Okay, everybody can see full screen, correct? All right. So we're going to zoom in a little bit. This is that exact cruise turbo. This is the intake housing from a cruise. And we're going to show you what happens. So this would be where the PCV hose comes off of it, and we're going to show you what happens when an intake is restricted or an air filter is restricted. So I'm going to mute myself here for a second, and then we're going to do a little experiment here with this. Let's see. There is So does that make sense to everybody, what we just did and why?
Yes.
Okay, cool. That's a nice, easy experiment. So all we're doing with the tape is because obviously I can't in real time make a turbo or an air filter get dirty in real time. So it's no different though. As you tape off an air filter and it starts to get clogged, we're going to start putting vacuum here. When we start putting vacuum here, we are then in return putting vacuum on this right here, which in return is going to suck up this little check valve, because now you're going to have, as we saw, 9 psi of vacuum that's going to all of a sudden end up on this tube pulling on that rubber check valve. So what happens if it has this type of PCV system and it doesn't have a PCV built into the valve cover or built into the, well, that's built into the turbocharger? At that point, if you end up with a vacuum, what do you think happens? It's not going to go through the PCV system. It's not going to pull oil through that way. What do you think it'll do?
Pull it through the other seal.
There you go. So we're going to show you how that happens too. All right. Everybody can see that, correct? Okay, so this is the oil drain on it right here. We know that the intake side of the turbo can end up with a vacuum on it. There's going to be oil that's going to be flowing down through this. And when there's oil flowing down through that, it's going to be full. So if a vacuum is applied to this side of it, since we know that there's not an actual hard seal in it, it's going to be able to pull vacuum into the bearing housing. And we'll look and see what happens. Make sense to everybody?
Yep.
All right. So those are the most common ways for oil consumption to happen. Most of the turbos that would come back and be returned would be returned for those reasons. That was, and it's still really common because GM has multiple service bulletins about turbochargers being returned for that. Ford has multiple service bulletins, BMW, everybody does. So that's just something to think about. Now, the other side of that I can't duplicate for you is exhaust back pressure. You're supposed to have the same amount of pressure on the exhaust side as on the intake side as it builds boost to hold the bearing housing stable. If you end up with back pressure that is behind the turbo, so let's think about like a DPF that came apart, something is plugged, something like that. Now the turbo can't push oil out or can't push exhaust out. So the exhaust side of it is going to surpass the intake pressure side of it. And in return is going to start to push into the intake. And now we're going to push oil from the exhaust onto the intake side. The reason that I don't have any way to show you this is it's pretty dangerous to do. It's quite amazing how much pressure can be built by the exhaust of a truck. A friend of mine had a Duramax that a DPF got plugged in and it actually split a turbo in two. They put another turbo on it and didn't realize that that was what caused it. And then it started spraying oil out of the vane control solenoid on it. And we've also tried, my good friend and mentor, Mark Warren, plugged the exhaust on a rental car, on a Ford EcoBoost rental car, trying to duplicate this and ruined a turbo and in return sucked some parts of the turbo into the motor and blew up a rental car. So you don't want to do that. That's a problem. So it's very hard to duplicate. I can't show you graphs of what it looks like when it's plugged because I would probably blow something up. As we talked about, crankcase pressure is going to become a problem too, because if the crankcase is pressurized, then we cannot get oil to escape out. As you are replacing turbos, there's a couple things that I want you to think about. For your customers, for yourself, for the vehicle, whoever it is, I don't care. If you're servicing turbo vehicles, whether it be a Volkswagen, whether it be a BMW, whether it be a Chevy, a Toyota, it doesn't matter. The biggest thing is using the correct oil and then changing it on time. Telling the customer that they really need to let the vehicle idle down before they shut it off in hopes that it's also going to slow the turbo down. The oil's still going to be flowing across it, and then it's also going to help cool it a little bit. Making sure that the air filters are changed regularly. I would really prefer that they get changed on a turbo car like every 10,000 miles to make sure that we're never having the issue of a restriction. Change the coolant as preventative maintenance so we don't end up with rust in the bearing housing like I showed you. Now, the big one is to make sure, or I shouldn't say the big one, but the one that nobody thinks about is making sure that the battery state of charge is good. This is what I was talking about early on, and I said we'd touch on a little bit later. BMW has an issue where they will start to get rid of things. As the state of charge of a battery goes down on a BMW, they start to load shed and they get rid of things that they feel aren't necessary. One of the first things that they load shed is the after run of the coolant pump to continue to pump coolant through the turbo to help it cool. So if battery state of charge is low on a BMW, it's not going to run the coolant pump, and in return, it's not going to cool the turbo, and it's going to end up with premature failure. On GMs, GM will run the fans after the vehicle is off to try to help it cool the turbo. If it feels the battery is too low, it's going to turn those fans off to try to save itself, or maybe it's just going to die. So if the battery is not healthy, there's a chance that you can ruin the turbo, as weird as that is. So that's something to think about. Using the correct oil, not just a synthetic oil, making sure that you're using the correct type of oil and the correct spec oil is huge when it comes to turbochargers. So why are oil specs important? Everybody kind of thought that, they were snake oil, that they came up with it to sell more oil. Really, what it tells us is the additive package that's in it, what the manufacturer feels their vehicle needs in an additive package to live its best life throughout the time it's in use. So it wasn't something they just came up with to say, hey, we want everyone to use our oil. That doesn't matter, because the vehicle manufacturer is not in the business of selling oil. They're in the business of selling cars. Somebody else is in the business of selling the oil, and they are not the ones that came up with a spec. A manufacturer came to them and said, we need it to meet this. Maybe they run it during prototype. This type of oil doesn't work for it. The engine blows up prematurely. We switch to a different spec to get the engine to last longer when it's in prototyping, and then in return that becomes the spec when the vehicle goes into production. So different specifications may be used because they have specific additive packages. That's the thing that you need to remember. So this is a spider web chart. The center is 0 and it goes out to 10. This is put out by a company called Lubrizol. Lubrizol is not a oil company. They don't sell oil. They're an additive company, or a chemical company. So what this is showing is the difference of each additive package and what it is. We have, how good it is at preventing piston deposits, how good it is at preventing sludge and preventing wear and soot thickening, and is it compatible with after treatment? That's a big thing. Are you working on a lot of sprinters? Are you using an oil that per its spec is compatible with after treatment and DPF systems? Because the wrong spec oil, even though maybe it's a 1540, if you're working on a diesel sprinter and you're like, I put 1540 Rotella in everything. If it's the wrong spec and it's not created for a DPF engine, it's going to ruin the DPF. So to show you what I mean by that, this is the Dexos 1 spec. We've all seen the Dexos spec on GMs. That's something that we think about all the time. And we look at and we're like, yep, it says that we need Dexos oil, blah, 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 blah. We've all been using that. That's not a big deal. You can see it's really good at preventing wear, really good at preventing sludge, not so great at preventing piston deposits. And then with after treatment compatibility, it's really not very compatible with a DPF system. So then they came out with Dexos 2. As you can see, Dexos 2 is much different in the after treatment compatibility department. This is when you compare the two of them, makes it even more abundant. You can also see Dexos 2 is a oil that's made to prevent soot thickening and then made to be used with after treatment systems. So if you put Dexos 1 oil in, so let's say a Duramax, it's going to ruin a DPF or can potentially ruin a DPF. GM spec versus a Ford spec. This particular Ford spec is obviously not a diesel oil. It has no after treatment compatibility whatsoever. It's a fuel economy oil. This would be a oil spec that's for something probably maybe an EcoBoost engine or something, a small 4-cylinder engine. The European specs, you can see the difference between 2 Euro spec oils. So this is a perfect example talking about maybe like a Liqui-Moly or something, looking at the differences. So one, you can see, is really compatible with after treatment, and the other does nothing for after treatment. So maybe it's, I'm like I say, I'm just throwing the name Liqui-Moly out there because a lot of people use that in European stuff. But say you're using the same Liqui-Moly in a gas car and the same Liqui-Moly in a Sprinter, even though it's good oil, you may not be using the right spec. So that's something you need to consider, so you're not preventing or you're not creating failure of expensive DPF systems. The specs aren't hard to find. I just wanted to put a couple slides in of where the specs are. This is in MotoLogic. You can see it says licensed to the Dexos 2. That's what it's looking for, is a Dexos 2 spec. And Identifix, it shows SEO 21. In return, then you take that SEO 21, and easiest thing to do is Google it. When you Google it, you'll get, and it'll show you on all the different manufacturers meets, spec SEO 21, or meets manufacturer spec SEO 21. So we need to consider looking that up if we're working on a plethora of different vehicles. Not saying that you need to buy this specific factory fill oil for every single vehicle, but you do need to be aware, is my bulk oil that I'm using in this vehicle going to work in this vehicle, or am I doing my customers and myself a disservice where I could prevent or create premature failure? So installation checklist. This is kind of, once we're all done, we've had turbo failure, now we're trying to prevent having any further turbo failure. It's very important to know what you're working with and knowing the type of turbo that you're working with. So some turbos are variable geometry, some aren't. If it's variable geometry, maybe you're not supposed to move the housings. We'll talk about that in just a second. And the actuator is attached to the turbo and it should not be adjusted. So as you're installing that, I don't want you adjusting stuff. If the actuator's adjusted, maybe we'll end up too high or too low, or maybe it's got a EcoBoost engine and it's got 2 turbos, 1 for each bank. If one of the actuators is messed with, then it could create one bank higher boost than the other. So you also need to check and make sure that they open at the same thing. So even if you're just replacing 1 turbo, what I want you to do is, before you put that turbo on, I want you to put a hand pump on it and put it right on the actuator and pump it up and see at what PSI does it start to creep and move. And then I want you to go and hook up to the other turbo and pump it up with a hand pump and see what PSI that one starts to open at, because they need to be opening at the exact same pressure or you're going to have a problem. And there's service bulletins about that for Ford. They've had issues. I think it's a P0, for some reason 232 comes to mind. But just keep that in mind. The turbos that you don't want to move, you don't want to move the end housings on. Most of the Garrett electric VGTs. So if anybody works on Hinos, they have a electric VGT. The Cruise Duramaxes have a VGT. The Mercedes Sprinters have an electronic VGT. The way they're set up is at the factory, it's put on a flow bench, just like a high performance head. At idle, that vane position inside the turbo is in a set position. They start to move the housings, and in return, that moves the vane position, and that's when it's set at idle. So if you twist those housings on one of these Garrett turbos, you've now adjusted it out of position, and there's no way to get it back to the correct position without having it on a flow bench. So know that you need to read about the turbo. Can I adjust this, or should I not touch it? Do I just need to bolt it on and not check anything? The other thing that I need you to check is to make sure that the compressor wheel turns okay. So without oil in it, and it's always going to have, or should have, some oil in it. If it's coming from a reputable rebuild facility, every single turbo should have some quantity of oil. It could obviously drip out over time if it's been on a shelf for a long period of time, but that turbo should have been ran as a cartridge and had oil run through it to balance it. So if it's had oil run through it, your tightness, axial and radial play in it is going to be pretty tight. You shouldn't be able to move it and touch the housing at all. If you get a turbo and it's dry, it's going to feel like you have a lot more movement in it. It still shouldn't be able to move enough to touch the housing. If it moves enough to touch the housing, that turbo is not built correctly, and it needs to be sent back. So don't install. I want you to grab it, move it this way, move it this way, move it up, move it down. Make sure that it doesn't hit the housing. Again, some of them are going to feel like they have more play if there's no oil in it, but they should all have been ran with oil, and the oil is what takes up the clearance between the bushings and the bearing housing, and then that tightens it up. So the amount of play is always going to be there. The spec is different for every turbo, although they're not totally crazy. They're still different per each turbo. So giving you a spec that is proprietary isn't really going to help you. The other thing I want you to do is make sure that the exhaust flanges are flat. In the rust belt area, turbos get sent back and the flange has to be refaced. Sometimes they'll escape without getting faced correctly. Sometimes, they might not be done properly or something like that. Or maybe you're putting a used turbo on. I don't know why you would do that, but if you're putting a used turbo on, maybe the flange is a little bit rotted. And at that point, you can end up with exhaust gases escaping. And that's the one way you can end up with fuel trim codes from a turbo problem, would be from that. If you want to know more about using fuel trim diagnostics to tell if you have a bad turbo, because that's a kind of important thing, and there's a lot of diagnostics, I guess I would say, that go into that, looking at data. I go over that in the 4-hour class. So know that the only way that you can have a fuel trim problem from a turbo is the mounting surface of the exhaust flange. That's the only way you could have that. So if you want to know more about that, check out the other class. Make sure that there's no debris in the exhaust from the original turbo. Make sure the converter or DPF is intact and isn't broken up. It's quite amazing when, let's say, a wastegate comes off of a turbo, or really anything comes out of a turbo, it goes in with such force. Typically it breaks whatever is behind it. So if there's a DPF or a converter there, most of the time it will have broken or ruined that. When that happens, sometimes you can end up with a situation like this. This is on a 5.9. Engine came apart, blew up the turbo. They put an engine in it, called me to look at the turbo because the turbo wouldn't spin. I went and looked at it. All of this debris not only was in the turbo, but was downstream in the exhaust as well. So if they had started it with a new turbo on it, it very likely would have came back up into the turbo and then ruined the new turbo. So you need to make sure all the debris from whatever failure is gone. You need to make sure there's nothing in the intake. You need to make sure there's nothing in the exhaust. A lot of the failures I also saw, or repeat failures of turbos when I was rebuilding, was maybe an exhaust valve came out, ruined the turbo that was the first failed turbo. They put a new turbo on it, never cleaned the exhaust, and pieces of the valve were still up in there, and then the valve would come in and ruin the new turbo. And then they'd send the turbo in saying something was wrong, and I would take the turbo apart and find more pieces of valve in it. So always do yourself a favor and make sure that you don't have any debris. Lastly, parts that I want you to replace with every single turbo to make sure you don't have failures. I want the oil supply line and the gasket replaced on every single turbo, no questions asked. Do it because it is a very small oil gallery, and I showed you how small the oil gallery is in the bearing housing. Every oil supply line and gasket I want replaced. Every oil drain line and gasket I want replaced, because if there's sludge in that and the oil cannot flow out fast enough, as you saw in the video, then you can end up with an oil leak there too. So every oil supply line, every oil drain line, I want the air filter replaced on every turbo, just in case you can't tell it's that dirty. As you saw with the Cummins filter, it really didn't look too terrible, but the pleats were really dirty on the bottom of it. So just if you're putting a turbo on something, replace the air filter. Want the engine oil taken out of it and put the correct spec engine oil in so that the turbo has a chance to live. I also don't have written down here, but when you're putting that correct oil in, you should prime the turbo. So you're going to take a little bit of oil and put it into the oil pressure feed line, and you're going to spin the turbo over by hand. You can do this when it's on the bench prior to putting it in. The oil is going to drip back out of it, but at least at that point, you can make sure that the bushings have oil on it when you're going to start it the first time. Not a bad idea either to crank the engine for a long period of time to pump oil into the turbo before starting it. So maybe disable ignition, disable fuel, whatever, and crank it over for 15 seconds to build oil into it. Also want any rubber or silicone charge pipe connectors that are taken off. I want those replaced, and any clamps that are removed replaced. Reason being is if there was oil in a charge air pipe, now that silicone connector has oil on it and has the ability to blow off. The reason I want the clamps replaced on it is a lot of clamps at one point in time had little staples in them holding the clamp to it. They were aftermarket silicone pipes. Those clamps, as you take them on and off, will crack. And I've had them crack before on vehicles after they leave. They're a spring type clamp, so you can't really over tighten them unless you really mash it on there and compress the spring, but you're supposed to tighten them down until it compresses the spring a little bit, and the spring continuously holds pressure as it stretches and moves, but they can crack. So just replace them, do yourself a favor, especially if you're working on diesel stuff, because when they do crack, if it's on an ambulance or something like that, you don't want to go down that hole. So just replace that stuff on every single turbo. Everything in this list, just do it, quote it in the job, be done with it. So with that, that's all I got for you guys. Anybody have any questions on any of this? Either I put everybody to sleep or I did good. Nobody's got questions.
I actually do have a
No
question that has come up a few times recently, and it's more with aftermarket stuff, but I've seen it a few times on some of the diesel stuff. I know, like with some of the bigger aftermarket turbos you get into on tuner cars, stuff like that, you'll have anti-surge ports in the compressor housing.
Yep.
I've noticed the same kind of thing on a few of the diesel turbos. Is that just to, I know obviously we have throttle plates and a lot of the diesel stuff we're seeing now. Are they serving the same purpose, or is that more resonance? What are those ports generally for?
They're serving the same purpose. So they all serve the same purpose of they don't want turbo surge, because what happens with turbo surge is now you're building a lot of boost, and maybe that boost isn't going to be used. So turbo surge is typically pretty loud, also makes the vehicle run funny, and then isn't good for the turbo because it's essentially going to spike the boost pressure, or can spike the boost pressure, which isn't good for anything. So yeah, all serving the same purposes, just to, well, noise and longevity of turbos. Any other questions? Oh, Terry's got us. Look at you, got your mask on. He doesn't want to talk because he's out in public.
I had it muted. Sorry. Just finished dinner.
Oh.
Didn't realize I turned the camera on. Oh well.
I didn't get away with it. What was for
Hope I
dinner?
didn't break anybody's screen.
Yeah. Did you have something good for dinner?
It was wing night, one of the pubs here in Boone.
Nice. Very nice.
My group says hey.
Oh. Tell them all I said hello.
He says hello. But appreciate the class. You know, there's a few things there I didn't know, and heard a couple things that I need to look out for when I'm messing with turbos. So appreciate that.
Welcome. Tell Lucas you're just going to blow up every one of them now.
Well, the next turbo I do will probably be on his truck. So
Perfect.
Oh, we just need to set someone on fire with it. That's kind of our thing.
Yeah, no more vehicle fires at Lucas's shop. We're not doing that again.
No, we save those for you.
So I don't come up there anymore.
Oh, that's why you don't go there. Okay.
Yeah.
All right. Well, I'm gonna get off here so I can go home. But
Alrighty.
class.
Alrighty. And if there's no more questions,
See you guys later.
I'm gonna hop off of here too. So
All right, thanks, Tanner.
Yep. Thank you guys. Have a good night.
Yeah. Thank you, everybody. Just so you know, we do have a webinar coming up on Thursday, just doing an overview and Q&A of our apprenticeship program. That's at noon, and everybody is welcome.
Awesome. Thank you.
All right, everybody.
Thanks a lot, guys. Take it easy.
See ya.
Have a good night.